All right, welcome everybody. Today we're going to be talking about hash tables. Hash tables are by far and away my favoriteest data structure, and you'll see why if we can do a little comparison of the data structures we know and their running times. So the three primary operations we do on a data structure are insert, search, and delete. And if we can compare some of the ones that we know so far in this class, maybe we can see why hash tables are so cool. So how long does it take to insert something into a vector? What do you guys think? Big cam, I know, right? All right, fine. I'll stick it up in the corner here. Smaller cam. There we go. All right, even smaller. There we go. All right, so how long does it take to insert something into a vector? Order what? If you have 1 billion people into a vector, and you call pushback, how long does that take? Might be a trick question, if you know how vectors work. Either order 1 or order n, right? So if you have a vector of size 4, and you've got 10, 20, 30, and 40 in it, and you try inserting 50, what happens is it will do something like this. It'll double the size of the vector, and then it'll copy over all of the elements and then put a 50 in. And so what happens is with a vector, pushback is order 1. Now you might be like, wait, that's an order n operation though. Like if you have 1 billion people, you might have to do 1 billion copies. Yes. But you only have to do an order n copy every n operations. And so this is order 1. And it's called an amortized order 1. Which is not exactly the same thing as order 1. Order 1 means, like for a linked list, it's always going to be order 1 to insert at the beginning or middle or at the end, wherever you have a pointer to. For a vector, pushback is order 1 amortized. And that's a little bit different. It averages out to be order 1, but it sometimes will be order n. So if you insert at the beginning or the middle part of a vector, though, like if I wanted to insert here, how many operations would that take? If I have 1 billion people in my vector and I'm trying to insert into the beginning here, like I want to put a new person right here, then I have to move everybody to the right? So that guy has to move right 1, he has to move right 1, he has to move right 1. So how long does it take order n time to insert at the middle of a vector? How long does it take to insert into the middle of a vector, or the front of a vector? What do you guys think? It is in fact order n. Very good. What about searching? So you've got nothing sorted or anything like that. You just have a vector containing, tablet just turned off. You just have a tablet that is not working. There we go. All right, so you've just got a vector of numbers like that, and you want to just go through it to see if a number's in there. That is also order n. Very good. Because it is not sorted. If it's sorted, you can do it in order log n time. Okay. And then for delete, if you want to delete something from the end of a vector, you call popback. What is the running time of that? To delete off the end. It's also order 1, deleting off the end, and it's also order n, deleting from the middle somewhere. Okay. So what about a linked list? Okay. So linked list is if it's order 1 if you have a pointer wherever you're going to insert it to, because no matter where you have these pointers, you can always insert something between them, right? So you got 1 million people this way, you got 1 billion people that way. You just put a new person in here by just kind of linking everything up like this. And so it doesn't matter how many elements you have before it or after it. You can always just do a little bit of this, a little bit of that, and move the pointers around and then insert something into the middle of a list. What about searching a linked list? Again, it's not sorted or anything. You're just, you got to cruise through the linked list. What is the big O to search a linked list? What do you guys think? Bencourt coming in with a troll. How long does it take? Order in. Yeah, you just start at the beginning and you go to the end. So if there's 1 billion people in your linked list, then you have to go through all 1 billion nodes. Worst case to find it. It's worst case the thing is in the last place, right? Or it's not in the list at all. And then deleting it is also going to be order 1, right? If you have a pointer, wherever you can point, you can always delete out of a linked list by just doing a little bit of pointer math and a little delete thing. So what about a BST? And let's say this is balanced. A balanced BST. How long does it take to insert, search, and delete? So you got a BST. We have 7 people here. How many searches do we have to do to find anybody in the BST? To insert, search, or delete. What do you guys think? We got effectively 8 people here. It is not order n. Think about it, Aaron. Like if I wanted to ask you, is 25 in this tree? Am I going to go look over here and I'm going to look at here? Am I going to look here? I'm going to look here? No, not at all. If I'm going to search for 25, I'm going to go to the right here. I'm going to go to the left here. I'm going to find 25 in 3 steps or less. On a balanced binary search tree, you can find anybody in order log n time. And same thing goes for inserting. If I'm going to insert 26, go to the right, go to the left, and I see the spot is open here, and I put the 26 there. So I can go through this tree and log. The depth of the tree is what matters, right? And the depth of the tree is log base 2 of n. Okay. So then that wouldn't. This is not an AVL tree. This is just a balanced binary search tree. Word balanced right there. You can balance a binary search tree a number of different ways. An AVL tree is one example of a balanced binary search tree. This is not, however, an AVL tree. So you can do red-black trees. There's a whole bunch of ways you can balance a tree. And so inserting works the same way. If you're going to insert something, you basically search for that, and then if you find an open spot, you put it in there. So searching and deleting are also both log base 2 of n. And so that's pretty good. Okay. So based on these numbers, you can see that there's sometimes reasons to use lists. There's sometimes reasons to use vectors. There's sometimes reasons to use balanced binary search trees. There's very few reasons to use a non-balanced binary search tree. Those are not great. The unbalanced binary search trees are like linked lists, but worse. So, pretty much everywhere. So, but today we're going to be talking about something called a hash table, which is my favorite data structure of them all. Between it and vectors makes up pretty much all of my, not all of it, but like most of it, I would say between vectors, and we'll bold you and turn you orange and turn you orange and bold as well. These two data structures are my bread and butter. Okay. And the reason why is because hash tables, if they are done right, let's say, crispy brown hash browns. We'll call this like an unloaded. I'll explain what that means in a little bit. It's kind of like balanced on a BST. You get order 1 inserts, you get order 1 searches, you get order 1 deletes. Okay? So this is why I want my hash browns covered and smothered. This is why hash tables are amazing. So imagine we just put 1 billion people into a data structure. And I ask you, hey, is Aaron in that data structure? In a single operation, you could be like, yes or no. Just like that, instantaneous. This is not what the DMV uses, obviously, because it takes them so long to find somebody. But This is the reason why hash tables are so incredible. They are the fastest data structure at insert, search, and delete. They do come at a small cost, and the small cost is that table answered below. Do they preserve order? Vectors preserve order. Lists preserve order. So what does that mean, preserve order? If I were to tell you, hey, these people are lining up at the, to wait for a table at the restaurant, with a list, you can maintain the order that they arrived in, right? So Jones, party of 4, okay, you're up, you cross them off. Okay, Hernandez, party of 6, cross them off. Do binary search trees preserve order in the order that people arrive? What do you guys think? Nah, not really. They don't. I mean, it's no. You're correct, Ella, but they have their own kind of weird order. They're like alphabetized, right? It's not what we mean by preserving the order that things arrive, but they kind of have their own order thing going on. It's like you could look at the list at any time and get everybody alphabetized that's waiting for a table. Not super useful in that case, but that's actually why you would use a BST. If you constantly need the thing to be sorted, then that's the prime usage of a BST is that. For a hash table, the answer is no. They do not preserve the order that they were inserted in. Now you might be asking, like, how is it possible for you to do this? Like, it seems impossible for you to do better than a binary search tree. And I'll explain it to you in a bit. But Betancourt wanted to make a point that the name of the standard library thing is, oof, that just got really big all of a sudden. Let's move this bigger. Okay, there we go. So the name of the hash table is called unordered set. And there's also unordered map. This thing just formatting's all screwed up on it. Unordered set, unordered map, unordered multi-set, unordered multi-map. Now, let's, I guess, just fill out this table for everybody else. What is the name in the standard library for vector? If you were going to make the vector class in the standard library, if you want to use the standard library's vector class, what is the name of the vector class in the standard library? It's a very difficult question. No. Betancourt is trolling you guys now. Vector, yes. And then what is the name of the list class in the standard library? It is indeed a list. Anyone know what the name is for a singly linked list? It is not linked list, Betancourt. What is the name of the singly linked list class? It is not a queue. A queue is not on here. A queue is basically a vector that has order 1 inserting at the front. So for a singly linked list, we are looking for forward list like that. That is how you do a singly linked list. And it's fairly uncommon a data structure. You almost never use it. Okay. What about a balanced binary search tree? What is that called in the standard library? If you wanted to use the standard library's binary search tree class, how'd you do it? Bet. Indeed, it is called set. And there's map, and there is multi-set, and there's multi-map. And now there's a new one too, called like flat set and flat map and things like that. Technically, I think priority queue would count as a, well, it's not a binary search tree. Okay. We know a couple other things, which we'll just put down here somewhere. There's also DEX, priority queues, queue stack, queue. There's some more things, but we're not going to put them on our comparison list here. Okay. So this is, I'm going to copy this, put on Discord. Balance BST is the ordered hash. It is not a hash table. It is most definitely not a hash table. This is, why did that not copy? Copy. There we go. So that is now pasted onto Discord for you guys to take a look at. So the balance BST is a binary search tree. It's called set, map, multi-set, multi-map. The hash table in the standard library is called unordered set, unordered map, unordered multi-set, unordered multi-map. Okay. So, how do hash tables work? Let's do this. So let's say that I was going to be, I can probably just insert a new table. 10 by 1. Sure, why not? Wow, what just happened there? Try this again. Insert table, 10 by 1. There we go. All right. Insert blue, and let's make the font a little bit bigger. Okay, so we've got index 0, index 1, 2, 3, 4, 5, 6, 7, 8, and 9. Here is a hash table. It doesn't look like much. This looks like an array. It's an array. It's a 1D array. It's just a standard array of integers, maybe. And I've just written the indexes above it for convenience sake. So give me some values to insert into this hash table. Give me some integers. 42. All right. 32. Nah, I don't want to do that one. 67. Okay. 76. Cool. 101. Why not? And OneNote's being OneNote as usual. 150. Cool. All right. 69. Sure. 6. No. Okay, it's good enough. 23. All right. Good enough. Okay, so here we have, I've put some numbers into this hash table. You guys see the pattern here? Any guesses as to how I was putting things into the hash table? The 1-digit matches the index. Very good, Messick. Very good. So when you told me to insert 67, that went into bucket 7 right here. Okay. So 67 modulus the size of the array, which is 10, is the bucket that it goes into. So the key here is the bucket, or the slot, or whatever you want to put it, as is equal to the value modulus the size. Okay. So when I put 23 into the array, it went into slot 3. When I put 42 into the array, it went into slot 2. Okay? So ask me if a number's in there or not. Give me some search questions. We just did insert. Did you see that? It was one operation. Insert 67. There you go. Insert 23. There you go. Is 12 in there? No. Is 101 in? Yes. So searching, if you ask me if 101 is in there, 101 modulus 10 is equal to 1. So I go to bucket 1. If I could draw properly. I go into bucket 1, and look, here's 101. The answer is true. Okay. Okay. And so I just basically do the same thing. What if you put 21 in there? No collisions yet. We're just going to pretend there's no such thing as a collision yet. Does 23 exist? Well, 23 modulus 10 is 3. So we jump down to bucket 3. And sure enough, it is true that it's in there. So as long as there's no collisions, we can do this all day long. The trouble is, as some of you might have noticed, is that what if I tried putting, I don't know, 33 in there, right? If I try inserting 33, then 33 is going to have a collision with the 23 that's already in there, and that's when we get the interesting part of hash tables. But just imagine for a moment that we will have no collisions at all. Is it possible to guarantee that you will never get a collision on an integer like this? A collision is when, good question, Salah, is when two of them map to the same bucket. Like if I try inserting 22 right now, 22 modulus 10 is 2. I'm going to try inserting it into this slot, but the slot's already taken. That is called a collision. Okay. That makes sense? If you have two guys that are going into the same bucket, that is a collision. We're not going to talk about that quite yet, because that's actually where the complexity of hash tables come in. If you never have a collision, then they're actually really simple. You just put the number into the slot, and then later on, if you want to check to see if it's there, you just look at it and go, yeah, okay, yeah, it's there. No, it's not there. Easy. Okay. So, why 3 slots not filled? Why 3 slots not filled? Well, nobody told me to insert a 44 or a 55 or something like that. Okay. So if you told me to insert 34, then I would just come over here and put a 34 in there. Cool. If you told me to put in a 45, I'd insert a 45. Okay. So can I guarantee 58? Sure, why not? Okay, now we're full. Any inserts past this point are doomed to failure. So is it possible that I can guarantee that there will never be a collision with 32-bit integers, your standard integers? What do you guys think? No? Sounds like something Todd Howard would say at a press conference. How many buckets would I need, Jose? If there are 4.2 billion different integers, how big would my array have to be to hold all possible 4.2 billion integers? Yeah, about 4 billion of them. And each integer is about 4 bytes, so that'd be 16 gigs of RAM, give or take. Do you have 16 gigs of RAM on your computer? Actually, yeah, you probably do. You probably could do it, and you can actually do it a lot more compactly, because at that point you don't actually need to store the integers, right? You can actually just do this, right? How do I clear these values? No. Never change one note. Never change. All right. So insert table. Insert below. So we just do this. True, true, false, false, true, true, false. You guys see that? So you actually would only need 1 bit per number. And so you'd only need 4.2 billion bits, not 4.2 billion integers, just 32 bits each. And then you could get it down to about a half gig of RAM, which is not too bad. Like 500 megs of RAM is like, it's not bad, honestly. Like, it's not bad. So 500 megs of RAM is not terrible, actually. And so you just have a true or false for each one. And if somebody inserts like 9, I'm not going to draw 4.2 billion here. But, if somebody inserts 9, you set it to true. If you do search, you just go to bucket 9. You're like, yep, it's true. And if they delete it, then you just set it to false. It's not in there anymore. Do you guys understand? This is, do you guys see how that approach would work? You could just make a hash table of size 4.2 billion. And this is something called perfect hashing. What do you guys think? Can you repeat that? Yeah, I can make an array of size 4.2 billion. And each one of the elements in the array is either true or false. And so if I tell you insert 7 into this hash table, then you just go to bucket 7, array index 7, and set it to true, like that. And if you tell me to delete 7 from the hash table, then I could change it to false, like that. How much RAM does it take up? About 500 gigs. 500 megs, sorry, of RAM. Does that make sense, Sarah? You just make a very large array. When is this useful? Well, it's fast. It's super fast. Now it's a little bit wasteful of RAM. 500 megs actually isn't that much RAM anymore, but it's very, very fast. It is super fast. It's going to be the fastest insert, searching, and deleting you'll ever see, right? Because all you do is you just jump to that spot in RAM and be like, oh, yep, it's true. It's in there. However, we typically don't do perfect hashing. And if you don't do perfect hashing, then perfect hashing means you have one slot available for every single possible element you might ever add. So if you're not doing perfect hashing, then we're going to need to have some ability to handle collisions. Okay? And so let's try this. All right. I guess. Below. So somebody give me a number to insert. We'll start this over. We got an array of size 10. Right? Size equals 10. 5. So, Jose, what slot does 5 go into? What is 5 modulus 10? How many times does 10 divide into 5 with the x remainder? What is it? 5. Good. All right. So we have inserted 5 successfully. No collisions yet. So Hawkman, give me a number to insert into this. 10. Okay, what is 10 modulus 10? 10 divides into 10 one time with a remainder of 0. Okay? The remainder operator is the modulus operator. So it goes into slot here. So 10 goes in here. Okay? 10 divides into 10 one time with a remainder of 0. So 10 goes into slot 0. The remainder operator is what we're talking about here. So it'll be 20. Okay, here we go. So Sarah has given us a collision. So we're going to try and insert 20. 20 modulus 10 is 0 also. So we're going to try and go into bucket 0. Now we got a question of like what to do. So we are going to start off by teaching you something called linear probing. Okay. And so what happens is when you try putting a 20 into here, you're like, oh, that spot's taken. So I'm going to put it here instead. And we're done. And when you do a search, if you search for 10, you're like, yep, true. If you search for 20, then you check 10. And since it's not 10, you check to the right. And you're like, oh, there's a 20, and you return true. You keep doing that until you get to one of these open spots. Okay? So, yeah. So what happens is you can no longer do it in order 1 time. Now it's going to be order n time. So the more collisions you have, that's the worse the performance of your hash table is going to be. There's this concept called load. Load is equal to the percentage full the hash table is. Right now we have a load of 30%. It's 30% full right now. Okay. As the hash table gets more and more loaded, the performance is going to go worse and worse. Okay, so we're going to insert 22. We're going to insert 22. So what slot does that go into, Sarah? 2. No problem. All right, so what do we insert now? 21. All right, so 21 tries to come into slot 1. That spot's taken. So it goes to the right. That spot's taken. So we go to the right. That spot's available. And 21 goes into there. All right, we got a 43 from Messick. So 43 tries coming in here. That spot's taken. We go here. We put a 43 into there. Okay, so somebody give me another number. That's confusing. That's hashing. So yeah, if you have perfect hashing, you never need to worry about those collisions. Just the slot that it goes into is the slot that you check to see has this thing been inserted before or not. But when you get collisions, then you need a way of handling the collisions. So let's insert 99. Let's say 99 goes in here. You feel it's all wrong? No, you're just feeling that you're feeling what you're feeling is this order 1 performance transforming into order n performance. Okay. Doesn't this get exponentially worse? Yes, the runtime drops from order 1 to order n. Just like kind of like how with a binary tree, if you go from a balanced binary tree to an unbalanced binary tree, also known as the United Nations balanced binary tree, then the performance drops significantly. So for a hash table, hash tables only work well when they are unloaded. Okay, when you have no collisions, essentially, when you have lots of room in them, then their performance is really good. When they start getting more and more full, their performance drops dramatically. And what it drops to depends on how you do it. Linear probing, the worst case scenario is order n for everything. Okay. So wouldn't this mess up the search function? Sure. Let's search to see if 21 is in the thing. So we hash to here, and we're like, that's not 21. Go to the right. Is that 21? No. Go to the right. Is that 21? Yes, it is. Return true. And so all of them have to understand which form of hashing you're using. So if you're using linear probing, you have to go to the right, go to the right, go to the right, go to the right, until you find an unused slot. Then you can return false. So if we were to search for 30, let's say we're searching for 30, 30 modulus 10 is 0. Is that 30? Nope. Go to the right. 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 Is that 30? It's open. We return false. Order in performance. Worst case scenario drops to be you're going to look at every single bucket in the hash table. Okay. But as long as you have some open spots in there, then you're not going to search the entire hash table. You're only going to search until you get to an open spot. Okay. 21 is in slot 3 right now. So when you are searching for 21, you're gonna search here first, bucket 1. Okay. Search here next. Nope. Search here. Yep. Return true. So all of these beautiful order 1 running times drop off, become order n running times when the thing gets full. Okay. And also it's important to note that things will wrap around the right. So if I were to insert 109, what bucket is this going to end up going into? If it's on the slot, you return false. No, you don't return false. If it's not in the slot, you check the next one. And you don't return false until you hit an open spot. You can't do it immediately when you have linear probing. So 109, no, there is no slot 10. There's no slot 10. There's no, yeah, there's slot 9's taken. 109 cannot go into slot 9. That spot's taken. So which one does it end up going into? Eight? No, you don't go to the left, you go to the right. So which bucket is to the right of 9? Yeah, you're right, Jose. Which bucket is to the right of 9? 0. Not null, 0. And that one's full, so we check 1, we check 2, we check 3, check 4, check 5. Oh, we got an open spot. So 109 is going to come into here. All right. So Brereton, I'm going to now insert 50. What slot is 50 going to go into? 0? Originally, but that slot's full. So which one is it going to end up in? What slot is 50 going to end up in after all is said and done? We start by checking to see if this spot's available, right? And it's not. So then we check this one. Now one's not available. Now one's not available. Now one's not available. So which one do we end up in? It would, in fact, go into 7. So 50 would end up here. And for those of you that are like, wait, this is nowhere near its original slot. Yeah, that's the problem. That's why you don't want to use a hash table that's very full. So what the standard library does actually is it'll actually allocate a new array that's twice as big, and it's going to copy element. It's going to not actually copy elements. It's going to rehash elements over. So 99 would hash to 20 is slot 19, and 50 would go to slot 10, and 5 would go to slot 5. And so in the standard library, when the hash tables get full, and by default, they can actually get pretty full before they rehash everything. Once they get full, then it creates a new hash table that's twice the size or some multiplier, and then it rehashes all the elements over. So every so often, you will have an order n insert in a hash table. Okay, what about if we are going to insert 999? So what is the initial slot that it is going to hash to? If we're going to try and insert 999, runtime is back to order 1 after it rehashes. Yeah, something like that. So if we're gonna insert 999 into this hash table, what is the initial bucket that it is going to try to go into? Not the final bucket, the first one that it's going to try and see if it's full or not. 9, very good. Yeah, so it's going to try here. And then after it tries bucket 9, what's the next one that it's going to try? Which bucket is to the right of bucket 9? Bucket 0. And which one is it going to end up in after it goes through this order n process? It's going to check all of them and finally end up in bucket 8. Good. Now the thing's full. And so if we tried inserting in this now, we'd have to like throw an exception or something like that. Okay. So that is called linear probing. Do you guys understand that? Like as the thing gets full, the performance degrades quite badly. That makes sense? Like hash tables, like the big thing about hash tables is that you get a trade RAM for speed. That's the trade-off you make with a hash table. So the more RAM you throw at a hash table, the faster it goes because you get less collisions. Okay. So let's do a little bit of modular arithmetic here. This is kind of a CSI 26 topic. By the way, linear probing, which I teach right now, is actually taught at the junior level at Fresno State. So you guys can thank me for that. You're learning 11, 12. You guys are learning what a lot of colleges think is junior level computer science, but I think that freshmen can understand hash tables. It's not really that bad. And I teach it because look at that running time. Order 1, order 1, order 1. Like it is top tier. It is a top tier data structure. Like you do not, like you don't want to miss these opportunities. Like it's really important that you guys get good at hash tables. Okay. We're not doing double hashing right now. Okay. So let's talk a little bit about modular arithmetic. So where is Tipton here? Tipton, where should I put -1 in this hash table? Where do you think, what bucket do you think -1 should go into? 0? No, well, if it was 0, it would go into 0. Like I would put 2 here, I'd put 1 here, I'd put 0 here. So where do you think -1 should go? 12. Yeah. Good. Actually, I have 1 too many. How about now? I just dropped the size from 13 to 12. Size is now 12. Yeah, it is now getting into bucket 11. So -1 is going to go here. -2 will go here. Now you might notice something interesting about this. What is what is the remainder? Here's a question. What is -1 modulus 12? Why is the size 12 and there's 11 slots? So there's 12 slots. 0 is one of the slots. So there's 12 total here. Yeah. So what is -1 modulus 12? Now this is actually rather famously a place where Microsoft's calculator actually used to get it wrong. I don't know if they still do. I can't do negatives. -1. -1 modulus 12 is 1. Yeah, that's wrong. So let's see here. Let's just double check this. 5, -5 modulus 12 should be 7, and they give -5 as the answer. Yeah, that's just wrong. So yeah, Microsoft's programmer calculator actually doesn't do modulus properly for negative numbers. So 12. How many times does 12 divide into -1? You guys ever thought of that before, like doing long division? That is an interesting question, right? You can't have a negative remainder. That doesn't make any sense. Because the remainder is how many pieces are left over after you've divided in as many times as you can. -12? No. You can't have a remainder of -12. The only remainders possible when you're modulusing by 12 is 0 to 11. So what is -1 modulus 12? So 12 divides into 1 how many times? Or -1 how many times? Right? Kind of a weird question, right? What do you think? -1 times? Okay. -1 times 12 is -12. 1 minus -12 is 11. So the answer is -1 with a remainder of 11. See that? And that is why -1 goes here. That hurt your brain? You don't get it? Well, the remainder operator has to give you a number from 0 to 11. If you're dividing by 12, like if you have 63 slices of pizza, right? You have 63 slices of pizza and you're dividing it into 12 people. Each person gets 5 slices with a remainder of 3. So there's 3 pieces of pizza left over. You can't have negative pieces of pizza left over. Okay. So yeah, it's -1. It's -1 minus -12 is 11. And so with negative numbers, if you do the long division, if you said it divides in 0 times, you're going to have a negative number left over, which doesn't make any sense. Another way you can think about this, Sarah, is you can just look at it visually, right? So if you think about it, where does if I had the number of let's see here, 21, which bucket is 21 going to hash to? What bucket is that going to go into? What is 21 modulus 12? 12 divides into 21 one time with a remainder of 9. Okay? So it goes into bucket 9. It divides in one time, but remember modulus is the remainder operator. Okay? And so, OneNote's doing OneNote things again. Yep, can't click on the thing. Okay. So 21 is going to go into, no. You're doing your thing again. All right, I'm gonna have to reboot OneNote again because Microsoft can't make a good product to save their lives. All right, so 21 goes into bucket 9. All right, so Sarah, where is 22 going to go? What bucket is 22 going to go into? 22 modulus 12. I don't want to give you the answer. What is 22 modulus 12? Not 0. This is the remainder. 12 divides into 22 one time with a remainder of what? Yeah, Okay, look at the pattern. All right, where is 23 going to go? What is 23 modulus 12? 11. Okay, where is 24 going to go? 12 divides into 24 two times with a remainder of what? 0. You see how that works? When you walk off the right side of the thing, it wraps around to the left. And 25 would go here, and 26 would go here, and 27 would go here, right? And if you count backwards, it works the other way. 27, 26, 25, 24. You go off to the left, and you're now 23, spot 11, 22, 21, 20 would go here, 19 would go here. It's like a clock. Okay. When you add 1 to 12 o'clock, it's now 1 o'clock. When you subtract 1 from 1 o'clock, it's now 12 o'clock. Okay, they wrap around in both directions. And so by that logic, if you inserted 3, that goes into bucket 3. If you inserted 2, it goes into bucket 2. If you inserted 1, it goes into bucket 1. If you inserted 0, it goes into bucket 0. Where does negative 1 go? What do you guys think? Negative 1 modulus 12. Where does that go? This is why the Microsoft Windows calculators are wrong. You can't give an answer of 1 for this. It doesn't make any slight sense. Yeah, it goes here. Negative 1 goes here. Negative 2 goes here. Negative 3 goes here. Negative 4 goes here, etc., etc. Yeah, it goes backwards. Okay. Wraps around. So, where does negative 20 go? What slot is negative 20 going to go into? What do you guys think? 7? Negative 4 is the same as negative 16, negative 17, negative 18, negative 19, negative 20. No, it's going to go here. Negative 20 is going to go here. So, yeah, very good. Another way you can compute this is negative 20 plus 12 is negative 8. Negative 8 plus 12 is equal to 4. It goes into slot 4. So anytime this, you might be like, why am I adding or subtracting 12 to something? If I go 12 slots to the right from here, where am I going to be at? Negative 21 would go right here. Negative 21 would go there. Let's not worry about collisions right now. We're just trying to work on your modulus skills. So if I move 12 slots to the right, what slot am I going to be at? I'm at 4 right now. If I move 1 slot to the right, I'm at 5. If I move 2 slots to the right, I'm at 6. If I move 3 slots to the right, I'm at 7. 4 to the right, I'm at 8. If I move 12 to the right, where am I at? What do you guys think? There's a lot of people not saying anything on chat right now, by the way. If I move 12 to the right from 4, where am I at? Yep, I am back at 4 again. Exactly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm back at 4. So every time you add 12 or subtract 12, you're not changing the slot, right? So negative 20 plus 12 is negative 8, and negative 8 plus 12 is 4. So that's a very simple way that you can figure out what slot something's at. You just keep adding the size of the array to it. Contra-wise, if you wanted to figure out what slot, 26 was, you could subtract 12 twice off of it. So subtract 24 from it, you get 2. So that's another way you can do it without having to do long division, right? Because a lot of people are like, okay, I'm going to do 26 modulus 12. So I'm going to, put a 26 here, a 12 here, and that's a 2. And I'm going to multiply, and that's a 2. So it's 2 with a remainder of 2. Now you just subtract 12 as many times you want. You can add 12 as many times you want. and it doesn't change anything. So 26 subtracting 12, subtracting 12, subtracting 24, in other words, gives you 2. So very quick way of being able to compute these things. And you might think this is kind of weird. And you're right. Modular arithmetic is kind of weird. But it's very useful in computer science. Okay? So you will have an entire 2 or 3 weeks of this in CSI 26. Here's another question. What is 9 divided by 3? In this weird modular 12 world that we're talking about here. What is 9 divided by 3? What do you guys think? Take a wild guess. 3? 9 divided by 3 is 3. Got 2 votes for 3? We're not modulusing it. We're dividing it right now. So what is 9 divided by 3? 0? I don't think it's 0. Yeah, I think 3 is one of the possible answers, and we can verify this, right? Like if we do a little bit of algebra, 9 is equal to 3 times 3. Do you guys concur? Like, do you see what I did here? I multiplied both sides by 3, like that and that are kind of the same thing. You guys with me on this? I just multiplied both sides by 3. These are the, that and that are the same thing, right? Yeah. Okay. And so let's verify it. So 3 times 3. Okay, so we're going to start by going to 3, and 1, 2, 3, and then we go to we're going to go to the right 3 times. 3 times. We're going to right? Yeah. You see what I'm saying? We're gonna add 3 times. 3 times 3. It's adding 3 plus 3 plus 3. Right? So 3 plus 3 plus 3 is the same thing as 3 times 3, right? So we go to 3 to the right, to 3 to the right, 3 to the right, and we end up with 9. Yeah? That makes sense? Like, do you guys concur that we have verified that 9 divided by 3 is 3? You're probably wondering what the trick is here. Isn't this like 2nd grade math or something? What do you guys think? Do you concur? Like 3 times 3 is 9? What do you guys think? Apt observation? Okay. All right. Nobody's disagreeing that 9 divided by 3 is 3. Okay, cool. All right. I propose the answer is actually 7. What do you guys have to say about that? What? 9 divided by 3 is 7 in the world of Z12, in this world here. You don't believe me? Here, I'll do the same. I'll do the same algebra, right? It's just, So this is the same thing as saying 9 is equal to 7 times 3, right? So if we go to the right 3 times, if we go 7 to the right 3 times, so we go 1, 2, 3, 4, 5, 6, 7, get a 7, and we go 1, 2, 3, 4, 5, 6, 7, we get a 2. We go to the right 7, 1, 2, 3, 4, 5, 6, 7, we get a 9. There we go. So 3 times 7 is 9. And so if 3 times 7 is 9, then 9 divided by 3 is 7. And 3. So 9 divided by 3 is both 3 and 7. Right? 21 modulus 12 is equal to 9. Right? 3 times 7 is 21. Slot 9. So, it all makes sense, I think. I think we can all see this is true. All right, so 9 divided by 3 is both, it's both 3 and 7. There's two answers to it there. If you're in the world of Z12. If you're in this world where there's only 12 numbers, and you keep cycling around and you go off one side and go to the other, then 9 divided by 3 is both 3 and 7. So there you go. You got it. I think we're all clear on that now. This is something called modular division, and you don't have to know this right now. It's just funny because you get those really counterintuitive things. Like you get one number, 9 divided by 3 is 3. Yeah, okay, that makes sense to me because 3 times 3 is 9. But also 9 divided by 3 is 7 because 3 times 7 is 21 and 21 is 9. So this is actually the basis of modern cryptography. So if you're like, what's the use of this? As it turns out, modular division and the rules of modular arithmetic like this are actually sort of the foundation of RSA encryption, which is sort of the first modern crypto system we have. So you don't need to worry about that now. That's what you got waiting for you in CSI 26. It's exciting and fun stuff. Okay. So 9 divided by 3 is... So you're proposing that 9 divided by 3 equals 9. Let's see if that's correct. So 9 is equal to 9 times 3. It's equal to 27. 27 modulus 12 is equal to 3. Now, that is... Yeah, so this is equal to 3, actually. What is 1 divided by 3? Nah, modular is not a good word, not in this instance. It's usually a good word, but not in this instance. Yeah. Okay. Anyhow, you can have all sorts of fun with her. Like my wife once came in during the pandemic when I'm trying to explain to everybody why in class because they didn't believe me. I'm like trying to explain 8 divided by 2 is equal to 7. You know, and she just walks in and sees that and she's like, no, and she's like slowly backed away and just closed the door. She's like, I do real math for a living. don't corrupt me with that stuff. Okay, so linear probing. Do you guys understand that? If I were to insert 99, where would that go? Let's do one more example of linear probing. Where would 99 go? Everybody? What slot does 99 go into? Can't do division by 12 in your head? 96 is the nearest multiple of 2, right? So 8 times 12, right? Ah. So 8 times 12 is equal to 96. So 99 modulus 12 is equal to 3. Because it's 3 higher than the nearest multiple. So we are going to put a 99 in here. All right. What about 23? What slot is that going to go to? 23. Where would 23 go? Slot 11. Yeah, it's 1 less than 24. Right, so 24 would go here. So 23 goes there. Right? Or you can just say that 23 minus 12 is 11. Either way. There's lots of tricks that you can do like that. Okay, so we got a 23 there. We got a 99 there. I got the eraser on. Okay, let's make that 3 a little easier to read. There we go. Okay, where is 44 going to go? What slot is 44 going to go into? 44 modulus 12. Good. All right. 44 goes in here. That looks like a 49. 44 goes in like that. All right. Nope, it's not divisible. Only numbers divisible by 12 would go into slot 0. Right. So, all right. So let's try 27. So what slot is 27 going to go into? Originally 3, but we got somebody in there already. We got a squatter in our home. It's taking up slot 3. So what slot is 27 going to go into? Yeah, it's going to go into 4. Very good. So it's going to bump 1 to the right here. Okay. And if we were to insert 11, what slot is 11 going to go into at the end of the day? If I were to insert 11 into this hash table, where would it go? It is going to originally try to come in here. That spot's full, so it goes to the right and goes in there. Okay, I think you guys got this. So let me show you. One other way of handling conflicts. There's many, and I'll just show you kind of my favorite way of doing a hash table. And this way is with chaining. And so what you do, well, actually, let me just show you what it's going to look like. So give me some numbers. And I'll make this divisible by 10 again, just to make the tablet turned off again, just to make it easier on me. Okay, so give me some numbers. Give me some numbers to insert. 0. Okay. 420. 26. 2. 77. 430. 99. What else? 5. Okay. 69. 82. 24. I'm kind of running out of room up here. 35. It's getting crowded. What else? Wait, what is this? We are now doing something called chaining. Okay. And so you can either do this with a linked list, which is almost what it looks like right now, or you can do it with a binary search tree. Okay. So if you were to give me like, I don't know, -10 to insert, I would add it to a binary search tree here. -10. Okay. So what I have now with this type of hash table is every time there's a collision, they just get stuck on a binary search tree with each other. And so this is actually really easy to make in code. You just make an array of BSTs. That's it. So if I can write properly, that's it. And so every time you hash to a bucket, you just call the BST insert function on it. And if you want to search it, you jump to the right bucket and call search on it. And if you want to delete something, you jump to that bucket and call remove on it. So you have a forest of trees. You have, in this case, 10 binary search trees. But if you wanted to, you can make 1,000, 2,000 binary search trees, however many you want. And so as you get conflicts, the worst case running time on this actually degrades to order log n instead of order n, because it's a balanced binary search tree, right? So what you do on the server is you just I can just show you. You just be like a vector. You can make a vector of sets of integers like that, named hash table, like that, size 1,000. And so that just makes a vector of binary search trees. And then whenever you do an insert, you just do a modulus on the size 1,000 and insert into that binary search tree. So if all the trees are empty, then it's all good. And if everybody keeps hashing to the same bucket 7 or something, then the worst case time degrades down to order login like that. So it fills all the slots, then adds up to trees. Actually, each slot is just a tree when you do chaining. There is no, you actually don't put the values into the array. The array is like, it might just have like a null pointer or something like that in it. So you can do it as like a vector of pointers if you wanted to do it yourself, or you can just do it a vector of sets and just use the standard library binary search tree code and just make it that way. So it's I can probably whip it up pretty quickly. So you make a vector of sets of integers named hash table of size also something like that. And then if you wanted to insert something, so the index that it's going to go into, int index is equal to the value modulus the size. You can call that bucket if you want. So the bucket is equal to the number we're inserting modulus the size. So if we're going to be putting 900 in there, then it's going to go 900 modulus 1000, give you 900. So it's going to go into dot bucket dot insert x. Oh, that's returning an iterator. Yeah, contains maybe. Yeah. Okay, there you go. There's a complete working hash table implementation. So, can you have empty slots? Yeah, the trees will just be empty. So let's insert 10, 20, 30, 40, 50, and then let's search for 10. It's in there. Search for 33. It's not in there. Search for 50. It's in there. Search for 80. It's not in there. And there you go. So that is a complete hash table using implementation. So we just made an array of size 1,000, or a vector technically. We had an array of size 1,000. Each one of the buckets is a hash table, and then we just call insert on that bucket. This here is what makes it a hash table. Okay. So it instantly jumps to that bucket, and as long as there's no contention, we will be able to tell in order one time. Pretty simple, right? Like, it's not bad. Insert order 1, search order 1, delete order 1. But if you start getting contention on if everybody's hashing to the same number, then the performance will degrade down to login because we're using a binary search tree to handle the conflicts. So I like writing my code this way because this is the entire program, by the way. This is the hash table and its main handling input and everything. This is the entire program doing hash tables, and it is able to search and insert. I don't have delete. I could have added that easily. Order one time. Worst case, order login. Okay. Why did you learn the linear one if you can do trees with chaining? These are just common approaches that people take to doing hashing. So I like writing chaining because it's simple. It's the easiest to code, and it's got a better worst case time, right? Linear probing is kind of garbage, it goes from order 1 to order n, whereas this approach with BSTs drops to not, it's not even worse than this worst case time. You know what I mean? Like BSTs are pretty fast, hash tables are faster, and the worst it'll turn into is pretty fast. So, when you take a junior level computer science, though, they'll probably have you write a linear probing implementation, as well as quadratic hashing, double hashing. There's all sorts of other approaches that people take. Okay. This is how I think the Java language does its hash tables. I think they just do it like this, just an array of binary trees, basically. You like chaining better than putting the numbers in the wrong slots? Yeah, I like it better too. Especially, how do you delete, right? How do you delete with linear probing? That's tricky. So, sure, you can look at the code again. No, Fresno State has them writing linear probing right now at Betancourt. They're actually writing linear probing in junior level week 12 data structures at Fresno State. So. What do you guys think? You like it? I like it. I'm a professor. You need to agree with me. I'm kidding. This isn't a history class. Contain returns true or false if the number's in the binary search tree, right? So it'll if 30 is in that tree, then it will return true. If 30 is not in that tree, it'll return false. And so what we're doing is we just have made an array of trees, and we use the number to tell which bucket to jump to, and then that bucket is a binary search tree, and it inserts into that particular tree. It'll grow on you. It should grow on you, because you're a STEM major. If it's this simple and has order n, no, it's this simple and has order 1. Yeah, and this, unless you have a lot of collisions, which you're probably not going to have, at least not when you're typing things by hand. Yeah, it's going to be order 1. It's super fast, easy to code, super fast. A stem, like a tree. Yeah. The student made that in the previous class. I can't take credit for it. So, yeah, that's basically all you really need to know about hash tables, though, is the running time. We can go over how to do it in the standard library, maybe next class. And your homework assignment, by the way, I just gave you guys a little bit of debugging. So what you're going to do is become Aaron. So I pushed out a couple debugging assignments. I gave you a harder one just because. And this will be due at the start of class on Wednesday. These are pretty easy. What you're going to do is you're going to look through the code and try and find the bugs in them. So it's just a little. I typically give students about 10-15 minutes to do these in class. You got 2 days to do it. Still, don't wait to the last minute. There are 2 bugs in each one of them. There's one compiler error that's causing it not to compile. For example, it could be missing a semicolon, or maybe one of the semicolons is a Greek question mark. And then the second bug in each one is a logic bug. It's supposed to be computing the area of a circle, but it's actually computing the area of a square, that kind of thing. And so you have to find both the compiler error and the logic error for each of them. And these will be collected at the start of class on Wednesday. All right. Not black box. It is not black box. It is term 41. You have all the code. So we're just continuing our exploration of debugging and testing and things like that. There is no auto grader for it. You have to write the test yourself, figure out why it's not compiling, and once it compiles, figure out why the code is not working correctly. Okay. And this one, the first one involves vectors. Midterm 41 be tough. I'm giving you guys the harder version of this one. Interesting. This one is also a vector. That's a fun one. I remember that one. CD midterm 41C. And this one has a binary tree in it. So it's all using the standard library. Vectors, binary trees, that kind of stuff. Have fun. There are no Byzantine bugs. It is just a straight up compiler error, and it's a pretty straightforward compiler error. And then the logic error will probably take a little bit more thinking to solve. And then I'll see you guys on Wednesday. We'll do more hash tables. All right, peace out.